source attached to it. But yeah. Oh. Hello. But there are two boards. This board is the base board, and this board is the sensor board. So this one you would attach to the back of your car, so when you're backing up into your garage or something, it would send ultrasonic sound waves out, and if it reaches a certain threshold distance, it will send a signal over to this board, which would be inside of your car, and this buzzer over here would buzz and let you know that you're approaching your garage back. Oh, cool. Alright, yeah, so that's just a little diagram of what happens. So my main project was a balancing robot. And you can turn it on. Alright, so what does it do? It balances on two wheels by moving forward and backwards to compensate for its tilt. It resists my pushing. I have to push lightly because it's slightly unstable right now, but that's okay. And it moves around with remote control. And it should balance on an inclined surface the way I have my controls scheme now. I can't exactly demo it for you, but it does that. Alright, so how does it work? I have three main systems on my robot that are working together. So I have my Arduino here, that's the brain, it's in the middle. I have my two motors down here, and I have a sensor underneath that's really close to the axis of rotation. So what happens is the sensor reads the tilt, which is called the pitch angle, sends that to the Arduino, and it processes and does some fancy things and sends a command to the motors. So I'm afraid it will fall off the table. So we'll turn it off for now. So what fancy things are going on inside of the Arduino? Well, basically I have this thing called a PID controller. So when the robot is tilting, it needs to compensate somehow with the motors. So what it does is it uses proportional, integral, and derivative. It uses those three terms to compensate, and the way it acts on them is by calculating the error, which is my current position, which is upright, my current position, which is, measured by the sensors, minus my desired position, which is upright. So the proportional term will say, whoa, I'm tilting a lot. Let me try and compensate by driving forward. And my integral term will say, I'm really close to upright, but I'm not quite there yet, and my proportional term can't see it because my error is so tiny. So the integral term is integrating up my past error, and it will push me towards the set point where I want to be. And the last term is the derivative term, and that dampens the proportional term. You can see up there, if that blue line is the set point, I'm oscillating around it because I'm going forward and I see, whoa, I'm way too far forward, let me go back. And it goes back and forth and back and forth. So the derivative term will be able to say, let me look, okay, my slope is really large, so let me pull back on my control effort. So the way I have it structured in my code, so I have three nested PID loops. The outermost is for driving, the middle one is for balancing, and the innermost is for compensating for the difference in the motors. Because before, when I was testing it, my robot would turn because the same command would act differently on the two motors. So you can see it's not exactly tuned to perfection yet. It's still slightly unstable, but I can have remote control with this PS3 controller. It will connect. Alright, it's connected. I can ask it to move forward and move backwards. I can't push it too much further than that because you can see it's starting to go back and forth, which is what I was talking about with the proportional gain oscillating around the set point. I tried implementing turning. It's not exactly doing what I would like it to do because it will turn and then return to its original heading, which is not what it's supposed to do. It should turn and stay. So yeah, that's what I've been working on. Some challenges I had, the very first challenge was that the robot was jittering a lot. That was a huge challenge. We spent about a week trying to figure out what was going wrong. It turned out that my sensor measurements weren't clean. They were very jittery, so I had to clean them up. Yeah, we'll try to not fall off the table. Another issue was just tuning those PID loops because usually a lot of the PID tuning methods out there are for inherently stable systems, but this obviously is inherently unstable, which means that it was a lot of guess and check. Doesn't really suit my personality, but we had to do it anyways. I think what I learned from this project, it was a lot of first time I've ever worked with Arduino, first time I've worked with Docker cables, PSD controllers, a lot of these things. First time with procedural programming, so that was also interesting. But one of the things I'm pretty proud of is writing all of my own code. That was really awesome. It was cool to do one project and see it to completion all by myself and make sure that I understand all the components. I think I learned from this project to sort of have no regrets when you go forward with a change because it's better to change something quickly, realize it doesn't work, and roll back instead of sit there and say, okay, should I change? Maybe not. What if I break it? So yeah, those are some things that I learned with this robot. Any questions? Yes.
You say that you diagnose the sensors providing jittery readings. How did you diagnose it? What was the mechanism that you diagnosed that?
So Arduino provides something called, like, you can print out values in your code, but the problem with that is that you have a bunch of numbers scrolling by at like 60 miles an hour on your screen, which you really can't read. So I tried graphing those values instead with a processing sketch, and that was really useful. So I would lift the robot up and run the motors while tilting it and read the sensor readings, and it looked like this, like an earthquake was happening, which meant that the robot thought an earthquake was happening, so it would act like an earthquake was happening. And then originally I'd been using a Kalman filter, which is this super complicated linear algebra, I don't even know, sort of filter that should provide a good estimate of your current position. The issue was that I didn't tune it well enough, and there are a lot of things that went into tuning a Kalman filter that I really didn't understand. So we switched to a complementary filter, which was much simpler, single line of code, and it worked out really well. Yeah.
How many times per second does it check its position, and is there a limit of how low it can go before it works?
Well, I'm basically telling it to go as fast as it possibly can. I time the loop rate, and it's every 3 or 4 milliseconds. It's checking, calculating, and then spitting out a command to the motors.
You mentioned procedural programming, right? Do you elaborate on what that means?
Yeah, so I think there are like two main paradigms for programming, two main ways of thinking when you program. There's procedural programming that I think came first, and then there's object-oriented programming, which is what I'm used to. So in object-oriented programming, everything you write is a class, and it encapsulates its own data, and it hides information that other people really don't need to know about. And at least for me, because I started out with that, it looks a lot neater, and it sort of models how things are in the world, because we think of things as objects that have certain capabilities, and they have certain things that, like, descriptions that they hold. Whereas in procedural programming, everything is executed step by step, so my code got very messy very fast. More questions?
Thank you.
So right now we'll take a quick intermission for about 5 minutes before we